welcome back. So today we are going to talk about laminar non-premixed flames. Okay, laminar non-premixed flames happen when the fuel and the oxidizer are not mixed a priori. So that is a very natural situation, because even in nature or in engines, when you send a fuel stream inside a combustor, it takes some time to mix. Okay, and if the reactions are fast, you will have flames, of course, in a very narrow region which separates the fuel and the oxidizer, and those are basically called non-premixed flames. Okay, so non-premixed flames are common in terms of aero engines, and they have certain advantages, but they have certain disadvantages also. The advantages is that, as we will see, that they are very robust in the sense that their position, their stabilization is much more robust. That is, they will be found only where the fuel and the oxidizer will be at stoichiometric locations. But on the other hand, because of this stoichiometry, that is where the fuel and the oxidizer are present in purely stoichiometric conditions, there the problem is that the temperature is also will be very high. We will show this by analysis, and also as a result of which it produces much more emissions. So the temperature of non-premixed flame is difficult to control, and but it is quite robust in terms of flame stability. And so we will see. But the most important thing is that here in the non-premixed flames, you don't have to mix the fuel and the oxidizer a priori. So if you have a actual engine, like in a aero gas turbine engine, where you send a fuel spray through the injector, so the fuel spray will basically first atomize. That will the cylindrical spray will break up into small droplets, and then these droplets will evaporate, and then this evaporated fuel will actually mix, and then will mix and then the mix with the oxidizer. Rather, it will meet with the oxidizer, and these positions where they will meet, a flame can be formed. In this lectures, actually we will see how a droplet actually evaporates and burns, and how a non-premixed flame is essentially formed around the droplet. So in a sense that this topic today of non-premixed flames, and as you see that we will talk about the canonical structure of the non-premixed flames. We will see this canonical structure, that is a basic structure of non-premixed flames, and this gasification of condensed fuels and Stefan flow and droplet combustion. All these problems are of very high importance in terms of an air breathing aero engine, right? But you can always ask, as I keep reminding you, that of course the situation in an actual engine is much more complex, because in a gas turbine combustor, the Reynolds number, the turbulent Reynolds number is very high, because as the pressure is high, the density is high, and the Reynolds number is very high. Okay, and the combustion happens in a very strongly turbulent state. But then, as we will show later, that this, even the combustion happens in a strongly turbulent state, the fuel and the fuel air still there is the fuel air actually mixing is promoted by turbulence, but still we can think of, if we take the entire flame, we can find out segments of the flame in which this laminar structure, this laminar flame structure will be preserved. So to understand a unit flame, that is a fundamental building block of a big complicated turbulent flame structure, we need to first know how does a laminar flame structure looks like. So that is the importance of today's study, that to understand something complex, you have to understand the fundamentals first, right? You have to understand its basic structure first. So today's lectures is actually will be dealing with that. So we will dealing with the fundamentals of laminar non-premixed flames. That is essentially we will deal with laminar non-premixed flames. But you will see that here what we will study will go a long way in our understanding of what happens in a gas turbine engine, and which will come later. So in previous class we have seen that, before we go into what kind of problems we will study, in previous class we have done the governing equations and the constitutive relations, and also the coupling function formulation. So we will take those help of those governing equations and the coupling function formulations, and using those we will try to study these following problems and phenomena. That is, we will study the chambered flame. It is basically a a very ideal non-premixed flame. It is an example of a ideal laminar non-premixed flame in which there is no flow, there is no convection. Okay. Of course, in last class you have seen that even if there is flow, you can always find a small region near the flame, at the flame, where you can think that the flow is negligible, or the convective terms are negligible because they are of first order, and only the flame can be described between a competition between your diffusion and reaction. So, of course, one can do the idealization, but in this topic, in this chambered flame, we will assume that there is no flow as such, and only there will be like species diffusing. Of course, you remember that by flow we mean the flow bulk velocity u. When you say diffusion, we mean the diffusion velocity, that is capital VI, right. So, here in this chambered flame, we will only have diffusion in the sense that only species will be diffusing from two sides and will meet at the flame, and then the products will be diffusing out of the flame, and also heat will be diffusing out of the flame. So, that is the definition of, that is the description of a chamber flame. We will come into that. Then we will consider this condensed fuel vaporization and condensation. If you take a beaker, or if you take a vessel which is half filled with water, say, and then we continuously blow wind on the top of this vessel, so as to remove any fuel, any this liquid vapor accumulation, the vapor of the liquid accumulation, and then we will see how we can describe that. Of course, that is as you will see later, that this will be essentially a precursor to this study. So, we will then after we have done this study of condensed fuel vaporization and condensation, we will move on to droplet vaporization and condensation. All right. So, that is as you know that, as I have told you, that droplet vaporization and condensation is a problem of paramount importance for understanding any air breathing engines, because as we have seen previously that the most important fact that combustion is indispensable in air breathing engines is because of the fact that liquid fuels have extremely high energy density, and that is why you can basically in a small amount of mass you can carry a lot of energy actually. Okay. So, how do you get energy, how do you convert the chemical energy to thermal energy, the chemical energy stored in the liquid fuel to thermal energy? Of course, reactions in this cases does not happen in the liquid phase. So, first you have to basically convert the droplets or the liquid into essentially into fuel vapor, and then in the fuel vapor and the oxidizer can mix, and you can have a flame, and you can generate heat, and then you can do the accelerate that heated flow, and then can generate thrust, or you can use a turbine to generate the required power to drive the compressor, right. So, that is why this topic of this fuel vaporization and condensation is so very important. All right. So, we will go into these three topics today, and first the topic is this one, that is the first we will talk about the chambered flame. All right. What is a chambered flame? First we have to basically understand its structure. So, this is the structure of the chambered flame at different levels of complexity. Okay. So, here what is happening is that let us consider and focus on this part, that is in the top part. All right, that is this part. So, what is happening here is suppose on the left hand side you have a fuel region, pure fuel. How can you have that? Practically you can have a porous plug essentially. So, on that you can have a fuel region, okay, and which contains purely fuel, and on the then you have consider some space, some air in between, and then you have essentially an oxidizer region, okay. And now basically suppose you this fuel will, because here there is no fuel on and here there is no oxidizer, the fuel essentially will diffuse from this fuel region and will go towards the oxidizer region, and this oxidizer will go towards the fuel region. But of course, this is just by diffusion and not by bulk motion, right. Now, if you have a flame inside, the situation will change, because so if you have a flame inside, that is this is the flame, the situation will change, because now you basically have fuel will be consumed at the flame region, and you will also have oxidizer consumed in the flame region, and on and in return this flame region or the reaction zone will basically give heat out on both these two sides. The heat will conduct or diffuse on these two sides, and it will also the products will also diffuse on these two sides, okay. So, if in reality this region where this happens, in reality where this where where this reaction happens, that has a finite thickness. Okay, but at the same time this region is very small, because we have seen that because of the large activation energy, the reaction zone is always very thin. All right. So of course it will, but it will still definitely have some thickness. Now, if it has some thickness, what will happen is that we will have a structure similar to this, where the temperature will increase. T0, let us give the definition now. Let us say that the fuel mass concentration, pure fuel mass fraction, that is the mass fraction of fuel on this fuel region, is essentially YF0. Now, please keep this nomenclature in mind, because we will use this throughout this class. So, on the left hand side you have this fuel mass concentration, fuel mass fraction of YF0. Now, why is it not equal to 1? Because you can also have some inert in the fuel. The fuel can be a mix of, like, say, hydrogen mixed with nitrogen. Okay. So, then the amount of the mass fraction of fuel, mass fraction of hydrogen, is essentially given by YF0, whereas 1 minus YF0 is the mass fraction of nitrogen, like that. Similarly, on the right hand side you have basically the you have the fuel, we have the oxidizer, and the mass fraction of the oxidizer, that is a pure mass fraction of oxygen, is essentially YOL. Of course, this can have an air, so this is 1 minus YOL is equal to the mass fraction of nitrogen. All right. So, now let us say the left hand side temperature is T0 and the right hand side temperature TL. T0 is not equal to TL, because the fuel region and the oxidizer region need not be at the same temperature. All right. Now, let us say now you have a flame. So, if you have a flame, then the temperature, this is the region where the flame is. So, then the temperature will have a show a curve. Okay, and then the fuel, of course, the fuel mass fraction will decrease, and then it will decrease. But if there is a finite reaction zone, this will not be immediately not be 0, and there will be some reactant, some fuel leakage through this reaction zone. Okay, and then similarly this oxidizer will decrease, and then it will also slightly can leak through the reaction zone. Okay, but now we will not consider this description. We will just consider a simplified description, where we will say that basically we are taking a zoomed out view, where the reaction zone, we will not consider any thickness of the reaction zone. We will consider the reaction zone to be essentially a sheet, that is, the activation energy is so large and the reaction rate is so fast that the entire reactions is concentrated in a thin sheet of infinitesimally small thickness, and as a result there is no reaction zone, only a reaction sheet. And in that case, of course, your T0 and TL will have a sharp boundary within the of course, it is the temperature is not discontinuous, but it will be discontinuous in the derivatives. Okay. And then if the reaction, of course, if the reaction, this reaction sheet is an approximation of an infinite reaction rate, and then what we will say is that in this reaction sheet limit will when we say infinite reaction rate, we mean that the reaction rates are very fast compared to other processes in the system, essentially like diffusion. So, essentially this problem will be diffusion controlled, because the reaction time scales are very small, and of course, when the reaction rates are very fast, then everything is consumed as such, then there is no leakage. You see there is no leakage here, and then YF0 becomes 0 right after right at XF, which is the flame location. So, in this one dimensional picture, this is the this XF is the flame location. Of course, you can see that now it is clear why this is a one dimensional problem, because these regions are essentially are infinite in these both directions, in both this up and down direction. So, this problem is essentially one dimensional, and then the temperature increases up to the flame, then it decreases from the flame location to the right hand boundary, and then of course you have this oxidizer also goes to 0 at XF, and there is no oxidizer leakage from the from XF. So, that is an important point that we need to basically consider. So, beyond XF there is no fuel on the right hand side, and before XF there is no oxidizer on the left hand side. So, essentially the general structure, as you see, is the flame in this now we call this essentially a non-premixed flame. We got people also call this a diffusion flame because you see this problem is, we will see that essentially it is diffusion controlled, because the reaction zones are reaction rates are much faster than the diffusion process. So then the diffusion becomes a rate limiting step, and as such the problem becomes diffusion controlled, and people call this flame a diffusion flame. But that is slightly misleading, because that implies that premixed flames, in premixed flames diffusion process is not important, which is of course not true. In premixed flames also diffusion is important. In non-premixed flames or diffusion flames are also diffusion process is very important. In all flames diffusion is very important, and as a result of this we will call this, instead of diffusion flames we will call this non-premixed flames. Okay. So because you see that the reason is simple, because the fuel and oxidizer, they do not meet and they are not premixed a priori. Okay. So they only meet at, and they only get mixed at the reaction sheet of the reaction zone. So this general structure is essentially, going back, this general structure is essentially a thin reaction zone separating a broad fuel rich zone from the broad oxidizer rich zone. So this is much broad, this is much broad, this is very thin. Okay. So that is why it is we call this nomenclature. Now as we have seen that for infinitely fast reaction compared to diffusion, that is reaction rate itself need not be infinitely fast, we just consider it to be infinitely fast compared to diffusion. Okay. It is much faster than diffusion process, because as diffusion is a slow process, and the reaction zone shrinks to a sheet, and we call this becomes a phenomenon as diffusion control, we call this diffusion flame, but we will call this non-premixed flame, because as we said that both premixed flames and diffusion flames or non-premixed flames, both are diffusion controlled essentially. So and this is the thing where when we consider a finite but large reaction rate, that when the reaction zone becomes broadened and reactants leak to the flame, and excessive leakage will lead to extinction. So this is the reaction leakage phenomena that I was talking about. So you see that this does not go to 0 here, neither this goes to 0 here. All right. So from we will just recall the coupling function formulations previously that we did in the previous class. So we defined the stoichiometrically weighted mass fractions as this one, y tilde is equal to 1 by sigma in, yi divided by ynb. N is a reference species which is not defined yet, we have to define, it can be fuel, oxidizer, product, etc. B is the boundary location. So in this case the boundary ynb can be essentially yf0, where we consider fuel to be the reference species and B boundary to be essentially the left hand side boundary. Okay, I will come to this, and also this sigma in is the stoichiometric coefficient, and this is defined as the ratio of molecular weight times the difference of the stoichiometric coefficients divided by the molecular weight of the reference species times the difference of the stoichiometric coefficients. And then we defined a stoichiometrically weighted non-dimensional enthalpy and temperature, Hs tilde and T tilde, and these things are as you will see that essentially delta Hs and delta T are essentially delta Hs tilde and delta T tilde will be or Hs tilde will be essentially equal to T tilde minus T0 tilde will be same. Essentially these definitions will be very close, and we will use it interchangeably. And this QCN that is defined here is the chemical heat release that which is normalized by this Wn times W, the difference of the stoichiometric coefficients. We will come to this, and then we will see that here using this we will come we can define a non-dimensional, we can define a species enthalpy coupling function can be defined as T tilde plus yi tilde. Just to recall how we did this, if you remember that when convection in the flame zone we considered that the convection could be ignored because it was essentially a competition between diffusion and your reaction, and assuming that the process is steady state, we arrive at this equation, gradient of lambda by Cp times gradient of sensible enthalpy is equal to heat release rate. This came from your energy equation, and gradient of rho d I times gradient of yi is equal to minus wy, that is the consumption or production rate of individual species, that came also from your species equation, and these were like distinct diffusivity formulation. All right, and then if we consider a one-step combustion reaction, which is given by nu f tilde f plus nu O goes to, that is fuel. These are stoichiometric coefficients you already know. This is the fuel, this is oxidizer, goes to product in one step. Then we can define y f tilde is equal to y f by y f 0, whereas 0 is essentially our left hand side boundary, and y O tilde is equal to y oxidizer, mass fraction of oxidizer divided by sigma for the oxidizer divided by y f at the boundary. Reference, we have chosen N to be the reference species, and H s is equal to H s sensible enthalpy by y f 0 q c, and T tilde is equal to C p t divided by y f 0 q c, whereas q c, this chemical heat release, is nothing but summation k is equal to 1 to capital N H k enthalpy of formation, specific enthalpy of formation, molecular weight, this thing, divided by the reference species, which is our fuel. Okay, and then sigma I, because here we also define sigma, sigma I is nothing but, or sigma O is nothing but WO nu O double dash minus nu O dashed divided by WF mu F double dashed minus nu F dashed. All right, and then of course with this simplification we have already shown that we can arrive at this equations, that is Laplacian of Hs tilde is equal to Cp by lambda times Wn and del square yi tilde by Lewis number of ith species is equal to minus Cp by lambda times Wn, whereas Wn is equal to capital Wn times nu n double dash minus nu n dashed times y f 0 times this omega, which is the species independent reaction rate. We'll just write it here because it is not visible. Okay, and of course if this is fuel, or we can keep it actually as N, whereas N is equal to like fuel. Okay, you can write in terms of the fuel. Fine. So now then of course we see that if we add these two things, if we add these two equations, then the right hand side vanishes, and we can write as this as delta square beta I is equal to 0, where beta I is actually, instead of enthalpy, we can just write in terms of T tilde. That is because your what is your T tilde minus T0 tilde is essentially your Hs tilde, right. So that is why we can write this as in terms of your t tilde instead of hs tilde, and we can write beta is essentially equal to yi tilde by lei. So this derivation is involves much symbols, but is actually very straightforward. So I suggest you do this on your own, and then everything will become very clear. So but in the end, the advantage is that this whole complicated equation, you see, the beauty is that the whole complicated equation just becomes a Laplace equation, okay, with no with the right hand side equal to 0, and this is your coupling function beta I is equal to t tilde plus yi tilde by Lewis number I.